January 31, 1945, Clark Air Base, Luzon, Philippines. Major Frank T. McCoy's hands trembled slightly as he photographed the aircraft before him. An intact Mitsubishi G4M Betty bomber bearing the tail number 76312. This cannot be their standard design. No Air Force would build bombers in this way. The fuselage gleamed in the tropical sun, its distinctive cylindrical shape justifying its Allied nickname. Measuring nearly 20 feet from nose to tail, the bomber sat on the tricycle landing gear like a massive cigar resting on the tarmac. The wings, spanning 25 feet tip to tip, showed no battle damage. The engines, 14-cylinder radials producing 1,500 horsepower each, appeared intact. This was not a crashed aircraft salvaged from wreckage. This was a complete operational bomber abandoned by its crew during the American advance. But what had captured McCoy's complete attention, what would revolutionize American understanding of Japanese aviation doctrine, was what he discovered when he climbed inside the wings through the inspection panels. The fuel tanks were completely unprotected. No self-sealing rubber compound. No armor plating, no fire suppression systems, no protective coatings of any kind. Just thin aluminum skin, perhaps 2 millimeters thick, separating thousands of liters of high-octane aviation fuel from enemy machine gun fire. Major McCoy, commander of the Technical Air Intelligence Unit Southwest Pacific, had examined dozens of crashed Japanese aircraft across the Pacific. But nothing had prepared him for this moment. This bomber, abandoned intact during the American liberation of Clark Field, would expose a design philosophy so alien to Western military thinking that it would take months for analysts to fully comprehend its implications. The mathematics of this discovery would reshape American tactical doctrine and aircraft design for the remainder of the war. Every assumption American pilots held about enemy capabilities, about the price Japanese engineers were willing to pay for performance, about the value imperial forces placed on crew survival, was about to be systematically demolished by the evidence contained within this single pristine example of Japan's most important bomber. The journey to this revelation had begun 4 years earlier on December 8, 1941. That morning, as smoke still rose from Pearl Harbor, 82 G4M bombers and 26 G3M bombers lifted off from bases on Formosa. Their target was Clark Field itself, the primary American air base in the Philippines. The attack achieved complete tactical surprise. Arriving at 12:35 in the afternoon, the Japanese formation flew at $20,000 FET beyond the reach of American anti-aircraft guns. 27 bombers from the initial wave dropped 636 bombs, struck Clarkfield's runways and facilities. Moments later, 0 fighters swooped in at treetop level, their machine guns destroying every aircraft that had survived the bombing run. Of the 17 B-17 flying fortresses on the ground, 12 were destroyed outright. Nearly every P-40 Warhawk fighter was reduced to smoldering wreckage. In just 45 minutes, American air power in the Philippines had been effectively wiped out. Lieutenant James Harrington, one of the few surviving American pilots, watched from a bomb shelter as the Japanese formation withdrew northward. What struck me was how they came in, he later wrote in his combat report. Perfect formation, high altitude, totally beyond our reach. Then the fighters dropped down and tore us apart. We couldn't get a single plane airborne, but the Betty bombers themselves had departed untouched. The few American fighters that managed to get airborne arrived too late, finding only empty sky. The Japanese had demonstrated their bombers' exceptional range, striking from bases 460 miles away, a feat no American bomber could match at that stage of the war. The Betty's first year of combat proved devastatingly effective. On December 10, 1941, just 2 days after the Clark Field raid, 26 G4M bombers, joined by older G3M Nell bombers, attacked Force Z, a British naval task force built around the battleship HMS Prince of Wales and the battlecruiser HMS Repulse. The attack began at approximately 12:20 in the afternoon. Japanese bombers approached in coordinated waves. their torpedo runs executed with precision that stunned British observers. The Betty bombers carried Type 91 aerial torpedoes, each weighing 840 kilos with a 205 kilos warhead. These torpedoes were specifically designed for shallow water operations, running at depths that could strike ships even in coastal waters. The torpedo attacks focused on the two capital ships with devastating accuracy. Prince of Wales, a battleship displacing 43,000 tons and representing the newest generation of British naval power, took at least 6 torpedo hits along with damage from level bombers. The underwater explosions ripped massive holes in the ship's hull, flooding and overwhelming damage control efforts. The battleship began listing severely. Repulse, a battlecruiser built during World War I but modernized in the 1930s, absorbed at least 4 torpedo hits while attempting to evade the attacking aircraft. The ship's anti-aircraft fire shot down several Japanese planes, but could not prevent the coordinated torpedo runs from finding their targets. The cumulative damage proved fatal. Both capital ships capsized and sank within hours of the attack. Prince of Wales went down at approximately 1,320 hours, and Repulse followed at around 1,333 hours. British sailors perished. The survivors were rescued by escorting destroyers. The engagement lasted less than 2 hours from initial contact to final sinking. For the first time in naval history, capital ships actively defending themselves were sunk solely by air power while in the open sea. The G4M Betty bomber had achieved what naval theorists had debated for decades. British naval superiority in Asian waters was shattered in just 90 minutes. Across the Pacific theater through early 1942, American and Allied pilots encountered Betty bombers in every major engagement. The aircraft seemed to operate with impunity, striking targets at ranges that defied conventional understanding. They hit Darwin, Australia, from bases 2,500 miles away, demonstrating a reach that exceeded any Allied bomber's capability. They attacked Port Moresby from airfields across New Guinea's mountain ranges, maintaining pressure on Allied positions throughout the southwest Pacific. They struck Guadalcanal from Rabaul, a distance exceeding 600 miles, projecting Japanese air power across vast ocean expanses. The Betty's operational range gave Japanese forces strategic flexibility that Allied commanders struggled to counter. American fighters based at forward positions lacked the range to intercept Betty bombers departing from distant bases. Allied airfields came under attack from Japanese bases that were themselves beyond Allied striking range. The asymmetry in bomber capability meant that Japanese forces could strike at will, while Allied forces struggled to retaliate effectively. This advantage persisted through the first 6 months of the war. Betty bombers participated in virtually every Japanese offensive operation across the Pacific and Southeast Asia. They struck targets in the Philippines, Malaya, the Netherlands, East Indies, New Guinea, and the Solomon Islands. They supported naval operations throughout the theater. They conducted reconnaissance missions that exceeded the range of any Allied aircraft. The Betty became the symbol of Japanese air power's reach and effectiveness, but the advantage depended entirely on limited Allied fighter opposition. When Betty formations could strike without interception, when they could approach targets at high altitude beyond anti-aircraft range, and when they could deliver weapons and depart before fighters arrived, the aircraft proved devastatingly effective. These conditions characterized operations during the first half of 1942, when Allied air strength remained limited and dispersed. But by mid-1942, the tactical situation began to change. As American fighter strength increased, with Wildcats giving way to more capable Hellcats and Corsairs, and as pilot training improved and tactical doctrine evolved, Betty crews began reporting alarming losses. The shift became undeniable on August 8, 1942. 23 G4M bombers from the 4th Air Group departed Rabaul to attack American positions at Guadalcanal. American fighters intercepted the formation over Tsavo Island. In the ensuing engagement, 18 of the 23 Betty bombers were shot down. Approximately 120 aviators died in what would become the worst single loss of G4M aircraft during the entire campaign. Fighter pilots reported similar observations across every encounter. The Betty would erupt into flames with minimal hits. 2 or 3 rounds anywhere along the fuselage or wings produced catastrophic results. The aircraft quickly earned grim nicknames that spread through American squadrons. Flying Cigar, One-Hit Lighter, Flying Zippo, all references to the Betty's terrifying tendency to burst into flames from even light battle damage.
By October 1942, when Lieutenant Commander John Thomas Blackburn arrived at Guadalcanal to command VF-17 flying F-4U Corsairs, the Betty's reputation had completely transformed. The first time we caught a Betty formation, we couldn't believe how easily they went down, Blackburn later reported. Hit them anywhere along the fuselage or wings, and they'd explode. We actively hunted them, recognizing them as some of the most vulnerable targets in the Pacific skies. But the true extent of the Betty's vulnerability, the engineering decisions that made such catastrophic losses inevitable, would not be fully understood until American forces began capturing intact examples for detailed analysis. The first major intelligence breakthrough occurred in November 1942 when Australian forces overran Japanese airfields at Buna, Papua New Guinea. Among the abandoned aircraft, technical air intelligence units found Betty bombers with varying degrees of damage. Initial examination confirmed what pilots had reported. The fuel tanks had no protection whatsoever. Allied engineers with the Technical Air Intelligence Unit, SAFE West Pacific, conducted the first in-depth analysis. The wing access panels revealed fuel cells with no protective measures, thin aluminum construction, no rubber sealant layer, no protective coating, no fire suppression systems. Multiple Betty bombers examined at Buna showed identical characteristics. This was not battle damage or field modifications. This was standard Japanese design. The implications were staggering. By 1942, American bombers universally featured self-sealing fuel tanks. The B-17 Flying Fortress had incorporated them from the B-17C model onward, and the B-24 Liberator had featured them since the XB-24B prototype. Even fighter aircraft like the P-38 and P-47 included protected fuel systems. Self-sealing fuel tanks were standard. The layered rubber compound that swelled upon contact with fuel, when punctured by bullets or shell fragments, would seal holes, preventing fuel loss and fires. The technology added considerable weight to aircraft, but it dramatically improved crew survival rates. American military doctrine deemed this weight penalty essential and non-negotiable. Yet, here was Japan's primary land-based bomber, produced in the thousands and operating across the Pacific theater, with fuel tanks offering no protection. The weight saved by eliminating self-sealing systems, armor plating, and fire suppression equipment was immediately apparent, but the cost in crew lives became equally clear as loss statistics mounted with every engagement. The captured Betty at Clark Field in January 1945 will provide the most complete technical analysis. Major McCoy and his team spent 3 weeks dismantling and documenting every system. Their report, classified secret and distributed to all Allied air forces, detailed the Betty's extraordinary capabilities and catastrophic vulnerabilities. The G4M Model 1 specifications revealed an aircraft ruthlessly optimized for range and speed. Its empty weight was 6,741 kilograms, remarkably light for a bomber of its size. The maximum takeoff weight was 9,500 kilograms, with a fuel capacity of 4,780 L spread across 8 unprotected tanks, 4 in each wing, positioned in the wing center section, where they were most vulnerable to combat damage. The top speed was 428 kilometers per hour, approximately 265 miles per hour, and the maximum range was 6,340 kilometers, exceeding 3,700 miles. Its service ceiling was 8,500 m. The crew complement included 7 members: pilot, co-pilot, navigator, bombardier, radio operator, and 2 gunners. The design of the fuel system was particularly revealing. The 8 tanks were arranged in 4 groups of 2, positioned along the wing's longitudinal axis, where the wing joined the fuselage. This maximized fuel capacity by utilizing the thickest portion of the wing structure, but it also positioned the tanks directly in the path of enemy fire during combat. Any attack from the side or below would inevitably strike the fuel tanks. The aluminum construction provided no protection, and the absence of self-sealing compounds meant that even small punctures would result in continuous fuel leakage. American engineers calculated that the weight saved by eliminating protection systems exceeded 500 kilograms per aircraft. This weight savings translated directly into additional fuel capacity and extended range. But the cost of this vulnerability was equally calculable. Combat reports showed that Betty bombers hit anywhere in the wing area exploded with near certainty. The unprotected. The tanks created what engineers termed a critical failure point, a single system whose destruction would guarantee the loss of the entire aircraft. These numbers told the story of the design choices made in September 1937, when the Japanese Navy issued specifications that would define the G4M's entire existence. The top speed was 398 kilometers per hour, with a cruising altitude of 3,000 m and a range of 4,722 kilometers unloaded, or 3,700 kilometers carrying 800 kilograms of bombs or torpedoes. The requirements reflected Japanese naval strategy in the late 1930s. Japan's empire spanned vast distances across the Pacific, with naval bases separated by thousands of kilometers of ocean. The Navy needed bombers capable of striking enemy positions far beyond the range of carrier aircraft, bombers that could operate from land bases to support naval operations across the entire theater. Existing Japanese bombers fell far short of these needs. The G4M bomber, then in service, had a maximum range of approximately 3,000 kilometers. American bombers like the B-17 also had even more limited range in their early variants. No bomber in service anywhere in the world in 1937 could strike targets at the distances Japanese planners envisioned. The Navy's requirements were not arbitrary. They were calculated based on the distances Japanese forces would need to cover in any future Pacific conflict. From Formosa to the Philippines, 460 miles. From Repulse to Guadalcanal, 600 miles. From the Japanese home islands to potential targets across the Pacific, thousands of miles. The bomber that could meet these requirements would give Japan a strategic reach that no other nation possessed. But the requirements also reflected assumptions about future warfare that would prove catastrophically wrong. Japanese planners assumed that surprise and initiative would protect long-range bombers. They assumed that enemy fighter opposition would be limited by range and numbers. They assumed the war would be decided quickly before enemy industrial capacity could generate overwhelming force. All of these assumptions would ultimately prove false. The man tasked with achieving the impossible was Kiro Honjo, who led the Mitsubishi design team after taking over from Joji Hattori. Honjo had studied bomber design at Junkers in Germany during the early 1930s, absorbing European aeronautical engineering principles and manufacturing techniques before returning to Japan. He understood immediately that meeting the Navy's requirements would require compromises that Western air forces would never accept. Honjo assembled a team of engineers at Mitsubishi's Nagoya. Facilities were established to address the design challenges. The team analyzed every aspect of bomber design, calculating weight budgets for each component and system. They studied existing bombers from various nations, identifying areas where weight could be reduced without compromising structural integrity. They experimented with new construction techniques and materials that could offer weight savings. The mathematics were brutally simple. To achieve the required range, the aircraft needed an enormous fuel capacity. Each liter of aviation fuel weighed approximately 0.8 kilograms. With 4,780 L of fuel, the weight of the fuel alone would be about 3,800 kilograms at full load. To achieve the required speed with this fuel load, the aircraft needed to minimize weight. Every kilogram added to the empty weight reduced either range or payload capacity. These two requirements were in direct opposition. Fuel was heavy. Protection systems were heavy. Armor plating weighing hundreds of kilograms would be needed to protect crew positions and vital systems. Self-sealing fuel tanks added substantial weight due to the rubber compounds and additional structure required. Fire suppression systems added weight. Redundant safety measures added weight. The cumulative weight of adequate protection would prevent the aircraft from achieving the required performance. Honjo made a decision that would define the G4M throughout its service life. Protection would be sacrificed for performance. The fuel tanks would have unprotected aluminum construction, with no self-sealing compounds, no armor plating around the fuel cells, no fire suppression systems beyond basic fire extinguishers, and no redundant safety measures. Every kilogram saved would be reinvested into fuel capacity, range, and achieving the Navy's performance specifications. The decision was not made lightly. Honjo understood the risks. His team calculated the vulnerabilities created by unprotected fuel tanks. They knew that combat damage to the wings would likely be catastrophic, but they also knew that the Navy's requirements could not be met any other way with available technology. The choice was between an aircraft that met performance specifications but had known vulnerabilities, or an aircraft that failed to meet the requirements but offered better protection. The Navy had demanded performance. Honjo delivered performance. The first G4M prototype flew on October 23, 1939. The aircraft met every performance requirement the Navy had set. Speed exceeded expectations. Range surpassed projections. Payload capacity satisfied operational needs. The bomber entered production as a Navy Type 1 attack bomber, with Mitsubishi building the aircraft at plants in Nagoya. Initial production models, designated G4M Model 1, began reaching operational units in April 1941. By December 1941, approximately 180 G4. The G4M bombers were in service with the Japanese Navy. These aircraft would form the backbone of Japan's land-based air power throughout the Pacific War. The Betty's combat debut at Clark Field and against Force Z demonstrated the effectiveness of Honjo's design priorities in the specific conditions of early 1942. When facing limited opposition, achieving surprise, and operating beyond the range of enemy fighters, the Betty was devastatingly effective. Its range allowed strikes from bases considered safe by the enemy. Its speed enabled rapid penetration of target areas. Its payload inflicted meaningful damage. However, these advantages relied entirely on the assumption that Betty formations would encounter minimal opposition. Once American fighter strength increased, once interception became routine, and once sustained combat became inevitable, every design choice prioritizing range over protection became a death sentence to crews. The Guadalcanal campaign exposed a fundamental flaw in the Betty's design philosophy. From August to October 1942, more than 100 G4M bombers were lost, along with their crews, in a sustained bloodletting that the Japanese air forces could not sustain. The single mission on August 8 alone destroyed 18 of 23 bombers, killing approximately 120 aviators. The pattern repeated with brutal consistency throughout the campaign. Betty formations would depart from Repulse, fly 600 miles to Guadalcanal, engage American fighters, and suffer catastrophic losses. On August 9th, more bombers were lost. On August 10th, more losses followed. By the end of August, the 4th Air Group had been effectively destroyed as an operational unit. September brought no respite. Betty formations continued striking American positions at Guadalcanal, and American fighters continued to destroy them in overwhelming numbers. The mathematics were inexorable. Japanese forces needed to strike American positions to contest control of the island. Betty bombers were the only means of delivering significant strike capability from Repulse. But every mission resulted in losses that could not be replaced. October saw the pattern persist. American fighter strength increased as more squadrons arrived at Henderson Field. Pilot quality improved as combat experience grew. Tactical doctrine evolved to exploit the Betty's vulnerabilities more effectively. Japanese losses accelerated, even as the number of bombers available for missions dwindled. By November, when the Guadalcanal campaign effectively ended with the Japanese withdrawal, Betty losses exceeded 100 aircraft, and crew casualties approached 700 men killed. The exchange rate was unsustainable. Japan's most capable land-based bomber had been rendered obsolete by its own vulnerabilities. The Betty bomber had transformed from a feared weapon into what American pilots called easy meat. Japanese planners had expected losses, as all military operations involve casualties, but the scale of Betty losses far exceeded every projection. The unprotected fuel tanks that allowed a 6,000 kilometers range also guaranteed that any hit to the wings or fuselage would likely prove fatal. There was no middle ground, no wounded bombers limping home, no damage but survivable aircraft. The Betty bombers either returned intact or exploded in flames. By mid-1943, Japanese engineers recognized the need for modifications. Beginning with the 663rd aircraft produced in March 1943, 30mm rubber sheets were installed beneath the wing surfaces where the fuel tanks were located. These sheets were not true self-sealing tanks. They were a compromise, adding minimal weight while providing limited protection against fuel leakage. The modification reduced top speed by 9 km per hour and decreased maximum range by 315 km. However, crew survival rate showed no significant improvement. The rubber sheets could slow fuel leakage from small caliber hits, but they could not prevent fires from larger caliber rounds or cannon shells. They could not stop explosions when tracer rounds ignited fuel vapor. The fundamental vulnerability remained unchanged. Japanese designers made further attempts at protection with the G4M Model 3, introduced in October 1944. This variant featured actual self-sealing fuel tanks, with capacity reduced to 4,490 L to accommodate the leak-blocking material. The modification reduced the maximum range to 3,640 kilometers, a loss of more than 2,000 kilometers compared to the original G4M Model 1. Approximately 60 G4M Model 3 aircraft were produced by the war's end. However, the modification came too late and in too limited numbers to affect the Betty's combat record. By late 1944, American air superiority was so complete that no level of fuel tank protection would have allowed Betty bombers to operate effectively. The war's outcome had already been decided. The Betty's vulnerability became so notorious that American forces began using the aircraft to emphasize the dangers Japanese crews faced. On April 18, 1943, the Betty bomber played a key role in Admiral Isoroku Yamamoto's death during an engagement that highlighted both American signals intelligence capabilities and the aircraft's fatal weaknesses. American code breakers intercepted Japanese communications indicating that Yamamoto would fly from Repulse to Bougainville on April 18. The Admiral would travel aboard a G4M bomber with a fighter escort. 18 P-38 Lightnings from the 339th Fighter Squadron were assigned to intercept the flight, although only 16 aircraft actually flew the mission after one plane blew a tire on takeoff and another suffered drop tank failures. The mission required extraordinary precision. The P-38 would fly over 400 miles at wave-top height to avoid radar detection, navigate across open ocean without landmarks, and arrive at exactly the calculated intercept point at exactly the scheduled time. Any mistake in navigation or timing would result in mission failure. The intercept had to occur within a narrow window when Yamamoto's aircraft would be vulnerable. The P-38s departed Guadalcanal at 0725 hours, flying at 50 feet above the ocean for over 400 miles, maintaining strict radio silence. Navigation relied on dead reckoning and timing. The formation arrived at the calculated intercept point with precision that would become legendary in aviation history. At 0934 hours, exactly on schedule and 1 minute ahead of the calculated intercept time, the P-38 spotted Yamamoto's formation, 2 Betty bombers flying at low altitude, escorted by 6 Zero fighters. Captain Thomas Lanier and First Lieutenant Rex Barber broke from the formation to engage the bombers while the other P-38s held off the Zero fighters. Barber targeted the lead Betty bomber, which was carrying Admiral Yamamoto. The bomber took hits to the wing area, where the unprotected fuel tanks were located. The aircraft exploded in flames and crashed into the jungle. Yamamoto's body was recovered, and the following day it was confirmed that he had died from injuries sustained in the crash. The second Betty bomber also crashed, killing all aboard. The operation demonstrated multiple aspects of Allied superiority. American signals intelligence had intercepted and decoded Japanese communications. American planners had calculated the intercept timing with 1-minute precision over 400 miles of ocean. American fighters executed the mission flawlessly despite extraordinary navigation challenges. And the Betty bomber's vulnerabilities ensured that any successful interception would be fatal. There was no possibility of Yamamoto's bomber surviving once it was under attack. The unprotected fuel tanks guaranteed that any damage would be catastrophic. The Betty's vulnerability reached its most dramatic demonstration on March 21, 1945. 18 G4M bombers took off from Koya Air Base, each carrying an MXY-7 Ohka rocket bomb beneath its fuselage. The Ohka was a piloted rocket-powered aircraft with a 1,200 kilograms warhead, designed for kamikaze attacks against American ships. The mission required the Betty bombers to fly within 20 kilometers of their targets before releasing the Ohka aircraft. The Ohka pilot would then ignite the rocket motor and dive at speeds exceeding 650 kilometers per hour toward American ships. The warhead, 1,200 kilograms of explosives, would destroy any vessel it struck, but the mission depended entirely on the Betty bombers surviving long enough to reach their targets. The release range was critical. The formation departed Kanoya at approximately 1,430 hours. The 18 G4M bombers flew in tight formation, escorted by fighters, heading toward American naval forces off Okinawa. Each bomber carried an Ohka weapon beneath its fuselage, adding significant weight and drag, which reduced both speed and maneuverability. The bombers were even more vulnerable than usual, unable to evade or maneuver effectively while carrying the heavy weaponry. American radar detected the formation at approximately 100 miles. F-6F Hellcat fighters from the USS Hornet were scrambled to intercept. The Hellcats reached the Japanese formation well before it approached the release range for the Ohka weapons. In the engagement that followed, American fighters systematically destroyed the entire formation. The Betty bombers, already vulnerable in normal conditions, proved completely helpless while carrying the Ohka weapons. The added weight prevented evasive maneuvers, and the external weapons created drag that slowed the bombers. The unprotected fuel tanks ensured that any hit would be fatal. One by one, the bombers exploded and fell into the ocean. Not a single Betty bomber survived to reach release range, and not a single Ohka weapon was launched against American ships. 137 bomber crew members and 15 Ohka pilots died in the attack. The mission represented the ultimate demonstration of the Betty's fundamental flaw. An aircraft designed to deliver weapons to distant targets could not survive long enough to deliver those weapons when facing prepared opposition. The extraordinary range that made the mission theoretically possible meant nothing when the aircraft exploded before reaching weapon release range. The final mission flown by Betty bombers occurred on August 19, 1945, just 4 days after Emperor Hirohito announced Japan's surrender. 2 white-painted G4M bombers with green crosses departed from Sugi Airfield, carrying Japanese representatives to discuss surrender terms with Allied forces. The aircraft, with call signs Baton 1 and Baton 2, flew to Ishima, where the Japanese delegation transferred to an American C-54 for transport to Manila. The symbolism was profound and deliberate. The white paint and green crosses indicated peaceful intent, transforming the bombers from weapons of war into vehicles of diplomacy. The call signs Baton 1 and Baton 2 referenced the location where American forces had surrendered to Japan in April 1942, one of the most devastating defeats in American military history. Now, 3 years later, aircraft bearing those call signs carried Japan's surrender delegation. Lieutenant Den Sudo piloted one of the surrender aircraft, a G6M Model 1 transport variant converted from the bomber airframe. The transport variants retained the Betty's distinctive cylindrical fuselage and wing configuration, but carried passengers and cargo instead of weapons. The crew wore dress uniforms instead of flight suits, and the aircraft carried no weapons, no ammunition, and no military equipment, other than what was necessary for flight. The flight from Atsugai to Ishima covered approximately 1,000 kilometers, well within the Betty's range, even in transport configuration. American fighters escorted the White Betty bombers throughout the flight, ensuring they stayed on the prescribed course. The escort was both protective and supervisory, guaranteeing safe passage while preventing deviation from the planned routes. The White Betty bombers with green crosses became the final image of the aircraft that had opened the Pacific War at Clark Field in December 1941. The circle was complete. The bombers that had destroyed American air power in the Philippines during the war's early hours now carried Japan's surrender delegation in the war's final days. The aircraft that symbolized Japanese air power's reach and effectiveness now symbolized Japan's defeat and submission to Allied terms. The Betty's production statistics reflect both its importance to Japanese operations and the terrible cost of its design philosophy. Total production reached approximately 2,414 aircraft across all variants, although some sources cite figures as high as 2,435 when including prototypes and subtypes. The variation in total numbers reflects different methods of counting prototypes, subtypes, and transport variants. The G4M Model 1 made up approximately 1,172 aircraft produced from 1941 to early 1943. This variant featured the original unprotected fuel tank design with capacity of 4,780 L. Top speed reached 428 km per hour, and the maximum range of 6,034 kilometers made it the longest range bomber in service anywhere in the world. But the complete absence of protection systems made it catastrophically vulnerable once American fighter strength increased. The G4M Model II, with increased fuel capacity and slightly higher speed, accounted for about 1,142 examples produced from 1943 to 1945. This variant increased fuel capacity to 6,490 L, extending the maximum range even further. Top speed increased slightly to 437 km per hour, but the Model II retained a fundamental vulnerability of unprotected fuel tanks. The modifications improved performance but did nothing to address survivability. The G4M Model III, designated Model 34, was the only variant with actual self-sealing fuel tanks. Production began in October 1944, but only 60 to 91 aircraft were completed by the war's end, depending on the source. The self-sealing tanks reduced. The fuel capacity was reduced to 4,490 L in the G4M Model III to accommodate the leak-blocking material, resulting in a maximum range of 3,640 kilometers, over 2,000 kilometers less than the Model I. This modification came too late and in too limited numbers to impact combat outcomes significantly. The G6M transport variant, converted from bomber airframes, added another 30 aircraft. These versions carried passengers and cargo instead of weapons, serving in liaison and communications roles. The G6M Model I, used for one of the surrender aircraft in August 1945, represented this variant. Production continued until August 1945, with the final aircraft completed just days before Japan's surrender. Mitsubishi factories produced Betty bombers at peak rates of around 100 aircraft per month during 1943. Production slowed in 1944 and 1945 as Allied bombing campaigns disrupted Japanese industry, and resources were diverted to fighter production for homeland defense. These production figures made the Betty one of Japan's most numerous bombers, second only to some fighter types. Over 4 years of war, Mitsubishi delivered approximately 2,400 aircraft to Japanese Navy units across the Pacific. The bombers participated in every major campaign, taking part in key naval engagements and striking distant targets. However, production statistics only tell part of the story. The loss rates tell the rest. Few Betty bombers survived until the war's end. The overwhelming majority were destroyed in combat, consumed by the fires that the unprotected fuel tanks made inevitable. By August 1945, when Japan surrendered, only a few operational Betty bombers remained in service. The aircraft that numbered in the hundreds in 1942 had been reduced to dozens by attrition, a loss rate no amount of production could replace. The casualty statistics among Betty crews were similarly devastating, though exact figures remain difficult to verify. What is certain is that thousands of Japanese aircrew lost their lives in Betty bombers, their deaths made nearly inevitable by the aircraft's fundamental vulnerabilities. The unprotected fuel tanks created a situation where survival depended entirely on avoiding combat damage. Once hit, Betty bombers rarely survived. Once set on fire, they never survived. The crews understood these odds and flew anyway because military discipline and cultural values demanded they accept the risks regardless of the consequences. Surviving Betty crews were unanimous in their assessment. The aircraft's unprotected fuel tanks made survival a matter of pure chance. No amount of skill, tactical innovation, or courage could compensate for the inherent vulnerability built into every G4M. Former Flight Petty Officer Yamamoto, who completed 28 combat missions before being transferred to training duties, offered the most direct summary. The Betty was a magnificent aircraft that asked us to die for its range. We flew it because we were ordered to fly it. We died in it because that was what it was designed to make us do. The comparison with Allied bomber protection systems highlights a stark contrast in design philosophy. The B-17 Flying Fortress featured armor plating to protect pilot and co-pilot seats, with steel plates ranging from 0.3 to 0.31 inches thick. Armored bulkhead protected crew positions throughout the fuselage, while the bombardier's position featured armored glass. Waist gunner positions were equipped with protective shields. Self-sealing fuel tanks were standard from the B-17C model onward. Introduced in 1941, the B-25 Mitchell incorporated similar protection. Pilot and co-pilot seats featured armor backing, and fuel tanks included self-sealing compounds from early production. The B-25's empty weight of approximately 9,100 kilograms reflected the substantial weight penalty of these protection systems, about 2,000 kilograms heavier than the Betty. Despite the similar size and role, the weight penalty for Allied protection systems was substantial but accepted as necessary. American studies during the war demonstrated the effectiveness of crew protection measures with statistical precision. Body armor reduced thoracic wound fatality from 36% to 8%, a reduction of more than 75% in deaths from chest wounds. Self-sealing fuel tanks reduced fire-related casualties by similar margins. Aircraft equipped with protected fuel systems showed survival rates 3 to 4 times higher than unprotected aircraft when damaged in combat. Protected crew positions increased survival rates in damaged aircraft by shielding crew members from shell fragments and small arms fire. Armored glass prevented pilot casualties from head-on attacks. Bulkheads compartmentalized the fuselage, preventing fire or damage in one section from spreading throughout the aircraft. The comprehensive approach to crew protection reflected American doctrine that trained crews were more valuable assets than the aircraft itself, as planes could be replaced more easily than experienced combat veterans. The weight cost of this protection exceeded 1,000 pounds in most American bombers, but American industrial capacity permitted this weight penalty without sacrificing production numbers. American factories produced over 12,000 B-17 bombers and nearly 10,000 B-24 Liberators during the war. The production capacity meant that no matter the weight penalty for protection, Allied air forces could maintain the necessary numbers of aircraft to win. American forces could deploy large numbers of protected bombers without sacrificing operational effectiveness. Japanese doctrine, however, reached a different conclusion. The Betty's design reflected a belief that range and striking power outweighed crew survival. This philosophy was based on assumptions that achieving surprise and maintaining initiative would provide adequate protection. It presumed enemy opposition would remain limited and that the war would be short and decisive. All these assumptions turned out to be disastrously wrong. By mid-1942, American fighter strength had grown to levels that made intercepting the Betty a routine task. By late 1942, American pilots had learned to exploit every vulnerability of the Betty. By 1943, Betty formations suffered such heavy losses that their missions had become suicidal. By 1944, Betty bombers could no longer operate in daylight against American opposition. The war for the Betty bomber was written in fire and destruction. Every advantage that made it formidable in the early stages of the war became irrelevant once sustained combat began. Range meant little when the bombers exploded before reaching their targets. Speed was useless when fighters could intercept them from distant airfields. Payload became insignificant when formations were wiped out before even releasing their bombs. The analysis of tail number 763-12 at Clarkfield in January 1945 revealed the full extent of the Betty's flaws. The unprotected fuel tanks that had astonished Major McCoy were not an oversight or a temporary fix. They were a deliberate decision by engineers who believed that range was more important than survival. The designers had created exactly what their specifications demanded, an aircraft with extraordinary range and speed, built with minimal weight and optimized for the mission's requirements. The lack of protection in the fuel tanks made sense given the mission's focus on performance. However, this decision, made under constraints of 1937 technology and the assumptions about warfare at the time, collapsed when faced with the reality of sustained combat against an opponent with nearly unlimited industrial capacity and an advancing technological edge. The Betty bomber became a symbol of Japan's willingness to accept massive casualties in the pursuit of tactical advantage. It illustrated a military culture that prioritized mission accomplishment over the survival of its aircrews. When American engineers examined the intact Betty at Clarkfield, they weren't just analyzing an enemy aircraft, they were witnessing the physical manifestation of choices made years earlier. Choices that value performance over crew survival. Choices that ultimately cost thousands of Japanese aircrew their lives. The unprotected fuel tanks embodied this tragic cost as the aircraft capabilities were sacrificed for range and speed, while survival was deemed secondary. The tanks were not a mistake. They were a deliberate decision. The Betty bomber served from the first day to the last of the Pacific War. It sank capital ships, devastated air bases, and covered distances that no other bomber could match. But its true legacy is written in the lost statistics, which far exceeded all projections. The aircraft that opened the war by wiping out American air-powered Clark Field ended it by carrying Japan's surrender delegation in white-painted planes marked with green crosses. The crew of tail number 763-12 had abandoned their aircraft during the American advance on Clark Field. They survived by walking away from an aircraft whose design made survival in combat nearly impossible. Sadly, most Betty crews were not so fortunate. These men flew knowing the risks. They climbed into unprotected bombers, crossed vast stretches of the Pacific, and died in staggering numbers, consumed by fires of the aircraft design made inevitable. The story of the Betty bomber is ultimately about the cost of capability without protection. It shows that performance alone cannot guarantee success when that performance comes at the expense of crew survival. The remarkable range of 6,000 kilometers meant nothing when the aircraft couldn't survive the final 100 kilometers to the target. The impressive speed of 428 kilometers per hour offered no advantage when American fighters intercepted them from distant bases, aided by radar systems. The payload capacity of 1 ton was irrelevant when formations were destroyed before they could release their bombs. The Betty highlights that military technology, divorced from a realistic assessment of combat conditions, produces weapons that kill their crews as effectively as they strike enemy targets. The assumptions that underpinned the Betty's design about limited opposition and short-duration warfare were catastrophically wrong within months of the war's start. By the time these assumptions proved false, thousands of Betty bombers had already been produced or were in production, and Japanese industry lacked the capacity to replace them with better protected designs. Japanese designers understood the risks when they made their choices in 1937 and 1938. They calculated the weight penalties, they knew the vulnerabilities, and they accepted the trade-offs because they believed the performance advantages would prove decisive. They were wrong. Thousands of men paid the price for that miscalculation with their lives. The Betty's legacy goes beyond aviation history, raising fundamental questions about aircraft design, military ethics, acceptable risk, and the value of human life in warfare. American designers answered those questions by prioritizing protection, even at the cost of performance. Japanese designers, however, made a different choice. This difference stands as evidence of what happens when capability is prioritized over survivability, when range is bought with crew lives and performance takes precedence over protection. The thousands of burning Betty bombers scattered across the Pacific skies symbolize the consequences of that philosophical difference. They show the stark contrast between how different nations approach warfare in the Pacific. The U.S. designed aircraft to bring crews home. Japan designed aircraft to reach targets, regardless of the cost. In the end, the nation that valued crew survival built an air force that could sustain operations indefinitely. The nation that accepted catastrophic casualties for performance advantages created an air force that destroyed itself through attrition. The examination of tail number 763-12 at Clark Field confirmed what Allied forces had suspected for years. The Betty bomber wasn't poorly designed. It was brilliantly engineered to achieve specific goals. Those goals, however, did not include ensuring the survival of Japanese crews. And in that fact lies the entire reason why Japan lost the Pacific War.